This video will explain the concept of depth-dependent roughness, show how roughness is assigned to materials with SRH-2D, and give a comparison in results between the different roughness applications. We will start with a model for which we have already run an SRH simulation. Note that for this flood event, we see that around the lower portion of the model, the river floods some field and woods areas. We also see that the water depth is significantly varied throughout the area of the flooding. For this solution, the fields and woods areas were defined as materials having constant roughness values. In reality, for this situation, the field and wooded areas would likely have varying roughness with different depths of water. For example, the fields would have a higher roughness value with low depths of water, but once the water depth increases beyond a certain point, the field grasses and vegetation would mostly lie down due to the force of the water flow. Thus, we would expect that with greater depths of water, the roughness value imposed by the fields would decrease. Conversely, we would expect that with a greater depth of water in the woods area, that the roughness would rise due to the drag induced by increased foliage. We will assign depth-dependent roughness to these fields and woods material definitions, rerun the simulation using these new material definitions, and observe any differences in the results. We start by clicking on the materials coverage to make it active, selecting the Select Feature Polygon tool, and double-clicking on the Fields polygon inside the flooded area. This opens the Material Properties dialog for that polygon. Note that when the dialog opens, the Fields material is highlighted. The highlighted material is the one assigned to the selected polygon. We will change the Manning's roughness to be depth varied and click on the Define Curve button to specify a depth versus Manning's N XY series. The values may be entered directly, but for this video we will open a previously prepared file. There is a minor bug in the XY series dialog where it will display metric units even though we are actually using United States customary units. However, the values as shown in this dialog are what is saved in the SRH-2D input files. So as long as we keep our units consistent with the rest of the model, it will be fine. As we set up this XY series, we must take care that the curve's range includes the full extent of what we anticipate the depths to reach. We will click OK and exit the Materials dialog, and then do the same for the Woods polygon. Please note that the values used here are only examples used for the purposes of this video and may not represent actual roughness values. We can now run our SRH simulation and then compare results. Note that because we have monitoring points defined and linked to this simulation, a plot for those monitoring points is shown once SRH-2D begins running. As we fast forward through the simulation, we can observe how the values for each point become constant as the simulation progresses, suggesting that a steady-state solution has been found. With the solutions loaded on the mesh, the Dataset toolbox can be used to make difference calculations between the new and old solution datasets. For information about the data calculator and how it is used, there is another video which gives a thorough explanation. A link is provided in the description. For our convenience, depth and velocity magnitude difference datasets were previously prepared. Looking at the depth difference dataset, we see that a depth-dependent roughness had a significant effect, since the water level in the field area rose by up to half a foot in some areas. Water depth along nearly all of the upstream part of the model increased as a result of the variable roughness. The velocity in the fields area decreased by a significant amount as well, which is linked to decreased flow in the fields area and increased flow in the channel. From this example, we can see that varying roughness with water depth can have an important impact on the results of a model and is an important feature to consider when modeling with SRH-2D. This concludes depth-dependent roughness on SRH-2D materials. Please visit the Federal Highway Administration's website or the SMS wiki pages to learn more.